Welcome back here. Another quick video. What are we going to tackle today? How about a little polyatomic ion action here with our nomenclature? So polyatomic ions are interesting things. They are actually groups of nonmetals together that kind of has a charge, which makes them ions. And they have special names and they have special sort of formulas and charges that go with them. So for example, here we have NH4, NO3, and this actually contains two polyatomic ions. Just split it right about there. Over here, this is NH4 plus. That one nitrogen, four hydrogens move around as a unit because, well, they're sharing electrons. It looks something like this, basically. And overall, this thing has a +1 charge. And over here, there's also a polyatomic ion. That is NO3 minus. So that one nitrogen and three oxygens is carrying a -1 charge. And we'll give you a free sketch here. Why not? Give it the old college try. Go like that. Maybe a little action like that there as they are sharing electrons. Little brackets for good measure. And we have something like our nitrate actually here. Again, sharing electrons has an overall charge. So ultimately, this is still an ionic compound, which, as we talked about in previous videos, if you haven't watched those, we'll put a link here for you to watch them. But whenever we have an ionic compound, we want to equal 0. So that's +1 and -1, which means we just need one of each, which is how we get to our formula here of one of each of them. These ions here, which are polyatomic ions, have a special name. This guy is known as the ammonium ion. It is probably one of the few positive polyatomic ions that you'll see. There are a few other ones, but that's probably the most common one. This NO3 minus is the nitrate ion. One of the good things about polyatomic ions is they have fixed charges. Their charges never change, and their names really never change. So we just actually use the entire polyatomic ion name when we're using it. Doesn't matter how many of them you have, you just use the whole name. So that whole name there is ammonium. And this guy here is nitrate, and that gives us ammonium nitrate in this particular case. Now, a vast majority of polyatomic ions are actually negatively charged. And as I mentioned a second ago, this is probably one of your few positively charged polyatomic ions that you'll come across. So what does that mean? Well, that means you are most likely to come into this situation of a metal and a polyatomic ion coming together. And remember, as we talked about in those previous videos, again, take a look at them if you haven't. The metal involved in naming, that is where you should look. So what we're going to have here is we're going to fall back to our type 1, our type 2 metals. And basically here, our type 1 is our fixed positive charge guys, and our type 2 metals are our variable positive charge. The main difference is type 2 needs a Roman numeral because it could have more than one charge. Type 1 does not need it. So most cases you're going to have a type 1 or type 2 metal hooked up with your polyatomic ion, and then you will have to kind of follow the type 1 or type 2 ionic compound sort of rules for naming. So what does that mean if we took our Na and put it with our nitrate? Once again, split it right here. That is group 1 ion, which is sodium. That again is our nitrite ion. All together has a -1 to balance out the +1, Thus, we have one of each of them in the formula. We always want to look at the metal. Again, in this case, sodium group 1, fixed positive charge, tells us it's a type 1. And we just follow our normal type 1 rules, which means whole name of the metal, so that's sodium, and whole name of the polyatomic ion, which is nitrate, so that's sodium nitrate. Now let's say we had FeNO3 to the 3 in this case. Once again, metal, polyatomic ion, metal most important here. That is a transition metal, which means it's a type 2 metal. That means Roman numeral, and I need to figure out what's going on with the charge. So iron, I'm maybe not sure what it is. I do know my polyatomic ion here is nitrate, which is a -1 charge, again, like so. There is not just one of them, but there's actually 3 of them. So again, if you draw them out, one more, and one more makes 3. That gives me for my negative charge, -1, -2, -3. That means my iron in this case is carrying a +3 charge. That is a type 2. That is Roman numerals. That is full name of the metal. That is a Roman numeral 3 once again for the charge. Regardless of how many of these nitrates you have, it is still nitrate. Once again, we follow the same rule we talked about in a couple of videos at this point. No prefix. Again, because there's a metal involved. So no prefix in this case. You will very rarely ever see a prefix with a metal. It pretty much doesn't happen. So I wouldn't do it because you most likely will get one of those, a big X, which you don't want to do. Speaking of which, we do want to make sure we write our formulas correctly. So you may be wondering, or maybe asking, can I just write it like this? And the answer is no, because if you write it like this, that is 33 oxygens and 1 nitrogen, which clearly, if you look down here, is not what's going on. When you have more than one polyatomic ion, you do need to put parentheses around the polyatomic ion, and you do need to put the number you have lower right there of the parentheses to indicate how many of those polyatomic ion units that you do have. So there's a big list of polyatomic ions, which you could probably find. And if you're taking chemistry, you probably have that list. But when you look at the list, you'll find a number of things that will help you perhaps figure out how to memorize these guys. And that's usually for most people that are taking chemistry, it kind of has to memorize these polyatomic ion names and their formulas. There is a way to kind of do it or organize it to make it easier. So for example, if you're looking at a polyatomic ion list, you might see our NO3- that we just saw. That is 1 nitrogen, 3 oxygens. That is known as nitrate, AT. We have NO2-, 2 oxygens, 1 nitrogen. That is known as nitrite. You also might look on a polyatomic ion list and see SO4 2-. That is 1 sulfur, 4 oxygens, -2 charge. That is sulfate. SO3 2-. Again, 3 oxygens, 1 sulfur, -2 charge. Sulfite. In a grouping of 2 polyatomic ions that are related to each other, the one with the most oxygens will end in 8. The one with the least number of oxygens will end in 8. There is no other difference between these 2 polyatomic ions. This guy has 1 nitrogen, 1 nitrogen. It has a -1 charge, -1 charge. Difference is the number of oxygens. So typically the one with the most oxygens will end in 8. The one with the least number of oxygens will end in 8. So for example, PO4 3-, that is phosphate, AT, PO3, 3 minus. That is phosphite, IT. Again, they each have one phosphorus. They each have a -3 charge. Both same charge. Both have one phosphorus there. Difference is number of oxygens. So what's a good way to remember? Well, you could learn, for example, all the eights and know that the ites are just one less oxygen. Everything else stays the same. So if you were to remember nitrate, but you need a nitrite, IT, you know it's the exact same except one less oxygen. Now you have nitrite, you have nitrate. You could also learn all the ites and know that if you wanted the eighth, you just add an oxygen. So if you remember the ites, like SO3 2 minus is sulfite, just add one oxygen to it, everything else stays the same. Boom, now you have sulfate. So again, to adjust from ite to 8, you add an oxygen. To adjust from 8 to ite, you lose an oxygen. So again, knowing that adjustment is a really helpful thing when you're dealing with polyatomic ions. Now, there are actually polyatomic ions that are actually groups of 4 that are related. Most common one most people see, ClO4 minus, ClO3 minus, ClO2 minus, and you probably guess ClO minus. Every single one of these has a -1 charge. The only difference between all these, they all have a chlorine. The only difference is the number of oxygens. We have 4 oxygens, 3 oxygens, 2 oxygens, and 1 oxygen. We broke this panel of 4 up in half. Everybody to the right-hand side has the least number of oxygens, which means we know it should end in ite. So this would be chlorite. This guy would also be chlorite. Now I know what you're saying to yourself, can't really have the same name for 2 different things, and you are correct. So in a grouping of 4, the one with the least number of oxygens will also begin with hypo. So that is hypochlorite. Coming the other way here, this is 3 oxygens, 4 oxygens. Again, the one with the most oxygens should end in 8. This would be chlorate. This would also be chlorate. Once again, the answer to your question, yes, you're correct. Cannot have same name for 2 different things. In a grouping of 4, the one with the most oxygens, in addition to ending with 8, we'll start with per. So that's perchlorate, chlorate, chlorite, hypochlorite. By the way, that is a halogen, which means if you swap out that halogen for some other halogen, now we have BrO3 minus. So instead of chlorate, that's bromine, this will now be bromate. BrO2 minus instead of chlorite, that is bromite. IO3 minus instead of bromate, that is now iodate, and so forth. So you can actually swap out any of the halogens for these guys, and they're named the same way. Now, what happens if you wanted to adjust? Well, again, whichever one you want to remember, if you started to remember this guy, the 8, and you need 1 more oxygen, gets you to the perchlorate. 1 less oxygen gets you to the chlorite. 1 more less oxygen after that gets you to the hypochlorite. So how could that be beneficial? I don't know. If you say remembered PO3 3 minus, that is, my friend, phosphite. Now, If I lose an oxygen or take off an oxygen, I'm left with PO2 3 minus. Again, nothing else changes but the number of oxygens. So that is the least number of oxygens. That's going to be hypophosphite. I run out of room there. Now, hey, let me add an oxygen to my phosphite. If I do that, I got PO4 3 minus. Instead of phosphite, it becomes phosphate. AT. Hey, just for the fun of it, let's add one more oxygen to get a group of 4. So one more oxygen would be actually PO5, same charge, 3 minus. And that is a group of 4, the most, per phosphate. So again, if you kind of know how to adjust, you could actually adjust anything by just knowing, either the 8 or the 8 and know how many oxygens to put on or take off. Other things that you'll see on that polyatomic ion table, like CO3 2 minus, that is carbonate. And sometimes we will put a hydrogen on it, hydrogen ion, and that gives us HCO3 minus. Minus 2 plus 1 leaves us a -1 overall. What do we just do? We basically put a hydrogen ion on it. This is known as hydrogen carbonate. Now, a historical sort of name that's used a lot still, instead of hydrogen, bicarbonate is sometimes used. You also see that with bisulfate instead of hydrogen sulfate. So sometimes bi is used instead of hydrogen, still used today, like sodium bicarbonate. There are some polyatomic ions like OH minus, CN minus, and actually end in IDE. So that is the hydroxide ion, and that is your cyanide ion as well. But a vast majority of your polyatomic ions will end in 8 or ite. So again, if we kind of put this together, FeOH2, that is a metal. That is a polyatomic ion. And that tells me it's ionic. Metal most important, transition metal tells me it's type 2, which means I need a Roman numeral. So we're going to figure out our charge here on the iron. I do know OH is OH minus, and I have not one but 2 of them. So that's going to give me a net -2, means my iron is +2. Iron Roman numeral 2 for the charge. Once again, does not matter how many polyatomic ions we have. We just use the name of it, hydroxide. Now, what happens if you have some names? Say you had some copper 2 chlorate. Let's say you had some sodium bicarbonate. We just talked about. So again, we want to look at what it is. So metal polyatomic ion means ionic, which means I should have some ions. Copper with a Roman numeral 2 means my copper is carrying a +2 charge. Chlorate here is our ClO3 minus. So once again here, we are putting together +2 and -1. We want it to equal 0. We actually will need one more of these chlorates. That is a -1, -1 is a -2 to balance out the +2. We could count it up, 1 copper and 2 of our polyatomic ions, because we have more than 1, parentheses, 2 on the bottom. And we would have our correct charge here and formula. Coming here, sodium metal bicarbonate, also known as hydrogen carbonate. And again, polyatomic ions, so it tells us it's ionic. That sodium tells me it's type 1 metal. Sodium is group 1, which means it has a +1 charge. Hydrogen carbonate is this guy. -1 charge, +1 charge, just need one of each. Little NaHCO3 in this case. So again, polyatomic ions, you sort of have to, in most cases, if you're taking chemistry, just kind of learn them and memorize them. Again, you want to organize them. Like I said, to learn all the eights and know how to adjust up or down oxygens to get to the other ones you need, or you can learn the ites and adjust up or down. Again, a majority of the time you're going to be hooking these polyatomic ions up with a metal. So really your question there is, do I need a Roman numeral or no Roman numeral for the metal? And again, always the whole name of the polyatomic ion. And doesn't matter how many you have, you really don't use a prefix. Where's the one place where you might see a metal with a prefix, since we're talking about polyatomic ions? Let's say we had Cr2O7 2-. That is a polyatomic ion known as dichromate. Let's just say you put it together with your friend potassium. We would need, in this case, 2 potassiums to balance out the -2 charge. 1, 2, K2, one of those guys, Cr2O7. This would be potassium because it is a group 1 metal, and the whole name of our polyatomic ion is dichromate. And you caught me after all these videos. There is a prefix along with our metal, and the reason it just so happens is part of the polyatomic ion name. That is probably the only time you will have a prefix with a metal, is if the prefix itself actually has a prefix. I'm sorry, if the polyatomic ion itself actually has a prefix in it. So if the polyatomic ion name has a prefix in it, then that is the only time you'll actually see a metal and a prefix kind of hanging out together. Other than that, if the polyatomic ion doesn't have a prefix in it, you should not put a prefix on there. We didn't really put this prefix on. It came with the name of the polyatomic ion. So that's really the only time you actually see that. All right, that wraps up a quick video about polyatomic ions. Hope it helps. And again, let me know if there's any other topics you want to know about in terms of chemistry. You can maybe make a quick video on. Thanks again for watching. Have a good one. Bye-bye.